Back. So for today, it's gonna be a shorter lesson, and we're gonna talk about the arc length. Okay. The arc length formula, which is defined in this way: if f prime it is continuous on this given interval a to b, and then the length of this curve y equals fx from point A, fa to the point B, fb is given by this integral format, which is integral from a to b square root of 1 plus the derivative of f and then square and then dx. Okay, and of course you know that you can also write the corresponding differential formula for this arc length. That is, okay, if you want to calculate it from a to x, because as long as your x is on this interval, you can always derive a function which is the arc length function, right? So anytime you assign a value for your x, and then you can get the corresponding arc length for that part. Okay, so now students might ask, okay, where is this arc length formula from? Well, let me briefly give you some basic idea about where this is from. Okay, so as you can see that, for example, if we I don't know, so if we have a function like this, okay, suppose this is f of x, and then we know that, okay, this is continuous, and then the first derivative is also continuous. Let's say from a to b. Okay, so now how do we calculate the this arc length? Okay, well, the trivial idea is, okay, if I don't know how to figure out the arc length at this moment, what I can do is, well, at least I can give a try to approximate it. Okay, but how do we do the approximation? Well, the most obvious approximation method you can think of is, well, is it possible that I can, I don't know, so partition my interval, let's see, into 3 equal length space. Okay, and then correspondingly I'm going to use the streak line to do the approximation. Okay, to do the approximation. And you can see that if I partition the interval into 3 equal lengths part, and then the approximation actually is pretty bad, right? But think about this: if I double the number of the partition, and you will see that and do you see that this approximation compared to the original one is becoming way better, right? And of course, we can repeat this idea to more and more. And eventually, think about it, if the number of the partition goes to infinity, and in other words, this is kind of like back to the Riemann sum again from calculus 1. If you take that limit as n goes to infinity, which is number of the partition goes to infinity, if that limit of that summation exists, that's going to be exactly the length of this arc, and then thus simplified form, which is exactly this integral we give it here. But still, where is this format from, right? We haven't talked about that. Well, now let's talk about that in a minute. So think about it. Let's suppose this is a part of this curve. If I drag it from here, okay, and then also you can think of, like, I am using this streak line, to denote the one approximation for the real curve here. Well, if I can, let's see that if I denote the x, the difference from this point to this point for the x coordinate as delta x, and then if I denote this part as delta y, okay. And then based on the Pythagorean theorem here, guys, do you realize that the length for this pieces, which is exactly delta x squared plus delta y squared, right? That's based on the Pythagorean theorem. Well, if we do a little bit more, so you can see that this is what I plan to do. If I factor delta x outside, that means I'm going to have 1 plus delta y over delta x squared times delta x. Okay, so if I factor that out, well, keep in mind that we learned that as the delta x becomes smaller, and then this delta y over delta x will be a good approximation of this dy dx, right? And then also the delta x is also equals dx, which is when we're talking about the differential. So if you put this as an integral form, that will give you is 1 plus dy dx squared dx, okay. And that is exactly what we have it here, okay. So that's a simple explanation about where this arc-length formula from, okay. So to apply this, it's pretty straightforward. But I want to make one more comment before we finish today's class. That is, when you take the derivative of the given function, and then you're going to square that, right? And then you're going to add a 1. So be very careful the position of this 1 plus f prime squared. It's under a square root, meaning there are some situations if you can simplify under this radical in terms of a square format, that will be the best scenario. Why? Because you have square, you have a square root, you can cancel it out, and then you can evaluate your integral smoothly, okay? So a lot of times we would like to give a problem like this to test you, how to simplify inside of this radical, okay? There is also some other situations where it's impossible to rewrite inside part in terms of one single square format. And under that situation, you need to seek for different techniques to figure it out, okay? And yeah, so hope you enjoy this short video and have a nice day.